Welcome to week 10 of the ma135 ma160 calculus. My name is Götz Pfeiffer and this video is about modeling population growth. So, to begin with, let me remind you about things we know about exponential growth and decay. Namely, that a quantity that grows or decays at a rate that is proportional to its current size grows or decays exponentially. And here on the side I have a few curves, a few graphs of exponential functions, mainly the e to the x function here in blue, and then the corresponding decay function e to the minus x in orange. That's how they behave. The e to the x function starts off slowly, close to zero for most of the time, and then it suddenly takes off and, as they say, goes viral. Now the reason for that is that, of course, a quantity A is proportional to a quantity B if the quotient of the two is a constant. If A over B is a constant k, some number k. And therefore, to say in words that y changes at a rate that is proportional to y itself is what we now know as a differential equation. An equation that involves y as a function of time and its rate of change, its derivative, and the proportionality here is represented through that constant k. We have a simple equation between y and its derivative, y prime equals k times y. We've also seen that this kind of differential equation is separable in the sense that we can separate the y from the t. Well, the t isn't very visible in this equation here, but still. Now we can move the y's all on one side and the t's to the other side, and then integrate the two sides of the new equation, one with respect to y, one with respect to k, and we find then that the logarithm of y is kt plus a constant, which by raising things into the power, by taking exponentials, gives us y is a times e to the kt, where a is plus or minus e to this power c. So that's how, through integration, this simple differential equation turns into that explicit function for y involving the exponential function, involving exponential growth. And this exponential growth can be used to model many natural phenomena. Let's briefly look at an example of exponential decay, a radioactive decay. The radioactive material strontium-90, which has its own Wikipedia page, has a half-life of about 25 years. This means that after 25 years, there's only half of the mass of this radioactive material left over. Let's try. So this is an example of a quantity that decays at a rate that is proportional to its current size. So let's try and find an equation, find a formula for the mass m as a function of t. Let's say we start off with 24 milligrams of this strontium-90 material, and let's use the information that we have. 25 years it takes to for half of the mass to decay. Set up a formula. Then we use this formula to predict how much is left after 40 years, or to estimate the time that it needs for the mass to be reduced to 5 milligrams. And since we know that this is exponential behavior, exponential decay, we know that the formula, the function that expresses m in terms of t, has this form of an exponential function. It's capital A times e to the power kt with some constants a and k. Setting t equal to 0 in this formula here makes the e to the kt equal to 1, and we see that the a constant is the value of m at time 0. That's the 24 milligrams here that we start off with at time 0. So we can set capital A equal to 24. Then we also know that after 25 years, these 24 milligrams have decayed to 12 milligrams. So we can set up an equation using the constant A already. 24 times e to the 25k, 25 being the 25 years in time here. That's m evaluated at 25 is half of the initial mass, which is 12. And that's an equation which now only involves k as an unknown, and we can solve this for e to the 25k, which of course is 1/2. I prefer to write this here as 2 to the minus 1, and if we want, we can take logarithms and solve this for k, which then is minus 1 over 25, the logarithm of 2. This minus here being the minus 1 and the exponent of 2, according to the laws of logarithms. And that is k is a negative constant, because we're talking about a decay phenomenon here. And that's enough to fully determine the formula for m of t. We now know that e to the 25k is 2 to the minus 1. So, substituting this for e to the kt in here, we find that m of t is 24 times 2 to the minus t over 25. And then we're in business. Now we can determine the mass remaining after 40 years by substituting 40 for t in this general formula. And we find that m of 40 is 24 times 2 to the minus 40 over 25, which, when you put this into your pocket calculator, comes out as 7.917 milligrams approximately. Or, if we're given the desired mass, like 5 milligrams here, and the question is, what is the value of t that corresponds to a mass of 5 milligrams? We can set up an equation, m of t equal to 5, where m of t is our 24 times 2 to the minus t over 25, and then take logarithms to solve this for t, and find that t is minus 25 times logarithm 5 minus logarithm 24 divided by logarithm 2, using the laws of logarithms, which I would encourage you to look up at this point if you're not too familiar with them. And this evaluates to 56.58 years. So approximately 57 years it takes for this radioactive mass to reduce to 5 milligrams. Now that's a typical way to work with these models of exponential growth or exponential decay. Starting with the observation that, well, starting with the decision that the process you're observing is modeled by such an exponential formula, because it can be described in terms of the differential equation that describes the growth rate as being proportional to the current size. You can then pick a few values to determine the constants in the general formula. Then you get a concrete formula that describes, that models this process. And with this concrete formula, you can then make predictions or analyze other aspects of the process. And that's the idea we're now going to apply to the growth of the world population. Let's ask the question, what will world population be in the year 2100, 80 years from now, 79. So in order to find a reasonable answer to this question, one can set up a strategy. And this start with a simple model for population growth, and if necessary we refine this, and let's denote, so now we want to have a function y of t, say, for the size of the world population at time t. In 1789, the English economist Thomas Malthus suggested that the world population fits into this exponential growth model, that the rate of change of a population, that's births per year minus deaths per year, is proportional to the current size of the population. That's an assumption that is reasonable, and it gives this differential equation y prime equals k times y. The rate of change is a constant multiple of the current size. So the solution of this differential equation has this form: y is a times e to the kt for some constants capital A and k, which we can try and determine. So looking back over the last 100 or 120 years, it can be confirmed that the exponential growth model is somewhat reasonable. Here are some data points. World population measured every 10 years between 1900 and 2020. And here in red there's an exponential curve fitted through these points, approximating these points. And the curve here has the form a times e to the kt, where a is 1.43 billion, I suppose, and the k constant is 0.1385. That's the formula for the curve, which apparently fits these numbers approximately. In terms of a doubling rate, it can be described as like doubling every 50 years. That's when I became aware of this quantity, world population, when I learned how many people there are in the world, it was 4 billion. And now, like 50 years later, it's almost 8 billion, twice as many. Doubled in 50 years. Anyway, let's look at this a bit more precisely. Let's use our differential equations and fit it to concrete data points. You can look this up. In 1980, the world population was 4.458 billion, and in 2020 it's 7.831 billion. Assuming that the Malthusian model fits, that the growth rate is proportional to the current size, let's try and formulate a model to estimate the population in 2000, like in the middle of this time range, and to predict the population for the year 2050. So in order to in order to set this up, let's decide that 1980 is 0.0 in time. Then, okay, let's measure the world population in millions. Then P of 0 is 4,458, and the other number we're given is 40 years later. That's P of 40 is 7,831. So P of 0 that's the A constant, and so we know that the population as a function of time has the form P of 0 times e to the kt. We need to determine the k here. Now that's a k which so remember we're measuring population in millions here, so that's to be kept in mind. Still, substituting the values we have, we find that with t equal to 40, that is e to the 40k, this value is P of 40 divided by P of 0, the 7,831 divided by 4,458, and that gives a k constant, taking logarithms, dividing by 40, as 1 over 40 times the logarithm of 7,831 divided by 4,458. That comes out as approximately 0.014. So that's a relative growth rate of 1.4%, and so we've determined our model. With this setup, taking 1980 as 0.0 in time and measuring the population in millions, we have P of t, we have a formula for P of t, which is 4,458 times e to the power 0.014085 times t. And if you want, you can simplify this by computing this exponential e to the 0.014, which then is 1.014185. So that gives a formula for P of t, a function of time. And with that under our belt, we can compute from the given data the world population in 2000 by substituting 20, which is the t value relative to 1980 of 2000, and evaluating p at 20 gives, now substituting 20 in the formula, gives 5,909 million for the year 2000. If you compare this to the figures on the Wikipedia, the actual figure was 6,143 million, so we're not far off. The actual figure was a bit bigger, but as you can see in the graph, there are fluctuations. The real story is not as simple as that, but roughly the model fits. And then for the year 2050, this is 70 years away from 1980, we can evaluate P at 70 and find 11.949 billion for 2050. That's roughly 12 billion, and that's about twice as many as the model predicts for 50 years before. So doubling over those 50 years. wait a minute, 12 billion in 30 years' time, and then doubling again over the next 50 years to be 24 billion in 2100. It's hard to imagine, is it? If you look up on the Wikipedia current predictions for world population over the next couple of years up to 2100, you find graphs like this. There's a variety of predictions, but what they all do have in common is that by no means the exponential growth will continue forever. Here the predictions are between a continued linear growth or even a decay that starts soon in the size of the world population. And if you think about it, in practice, exponential growth that goes on doubling all the time forever, isn't possible. There's eventually some limited resource will stop you from growing. And that's the basis for the predictions, for some of the predictions as they're illustrated in this graph here. The exponential growth that goes on forever doesn't exist. And so the next step for us will be to refine the model and take into account that the growth, that the description of growth as being proportional to the current size is too simple once these limited resources are reached. And this will be the basis of the logistic model, where we describe a quantity to the growth of a quantity to be proportional to its current size as before, but also at the same time proportional to the currently remaining resources. And how this is done precisely will be the subject of the next video.